Yes, okay. Yeah. Sorry, I can hear you very badly because of this displays here. Okay, shall I start? Okay, welcome to the second exercise class. So today our plan is to discuss three things. Hopefully we'll manage to get to them all. So they correspond to the exercise in the exercise sheet. So first we'll talk about quantum circuits, which is a way to describe the evolution of a several number of qubits in a graphical way. And we look at the examples of the gates for 1 qubit and also for several qubits. Then we'll see the experimental, one of the experimental ways to model, to create superposition of light beams, which is the Mach-Zehnder interferometer. And also we'll see how we can represent it simply by a circuit. And then finally, if we will have any time left, we'll try to do some very simple quantum computing on a platform. Okay, so let us start with quantum circuits and quantum gates. So as we've seen in the lecture, the evolution of a quantum state can be represented as a unitary. So the unitary is this matrix or an operator, which is equal, so which is obeys this law. So basically its inverse is its complex conjugate. So usually we denote this unitary as U. And the one of the examples of a unitary that can act on a two-level system, namely a qubit, is a Hadamard gate. So we usually call it H. It has the following form. And we can indeed check that it is a unitary. So for this, we just denote that first its complex conjugate is equal to H as well. And then we can calculate H conjugate. So it will be 1/2, 1, 1, 1, minus 1, 1, 1, 1, minus 1. And here it's just simple matrix multiplication. So first we have here 1, 1, 1, 1, 2. Then the second 1, 1, 1 minus 1, 0. Analogously here 0. And the final is 1 by 1 plus minus 1 by minus 1. So it's going to be 2. So this is just the identity matrix. acting on 1 qubit. Okay, how do we represent the action of this gate graphically? So for this, we can introduce the notion of a quantum circuit. So in a quantum circuit, we have 2 directions in which we draw. So one direction is the horizontal, and one direction is the vertical. So basically, in a horizontal direction, we draw from the left to the right the gates or the operations that are applied to a system. So the unitaries that are applied to the system. So for example, in this case, to represent the unitary evolution, which is described by this Hadamard H operation, we just draw it as an operation here. So usually the gates on 1 qubit is represented by this rectangle, and in the rectangle we see what operation we apply. And in horizontal direction, sorry, in vertical direction, from up to down, usually we just draw which systems are involved in the evolution. So for example, in this case, there is only one system, 1 qubit, to which this operation is applied. And then we can also label each of these lines, which correspond to each system, by the initial state of the system. So for example, we can say that this is the system S. Let's call it the system S. And we start in the state 0. And this is usually also a common notation of when we write the ket to denote to which system the ket corresponds. We also write the name of the system on the right of the ket, like as an index here. Okay, so how do we calculate the action of this circuit? So the action of this Hadamard on the system in the initial state 0. So for example, we want to know what is the final state of the system. So for this, we just write out how this evolution H acts on the system in the state 0. So this would be in a matrix form. We can write it as following. So this is the Hadamard, and then we acted on a qubit in a state 0. So can someone tell me which state we get in the end here? Yes. Plus. Yes, exactly. We get the plus state. Why? Because here we get the following vector. So the first component will be 1. The second component will be 1 as well. So this is 0 S plus 1 S, which is plus. Okay. Let us also see how the Hadamard acts. Yes.
Yes, it's just basically a placeholder for the name of the system.
Yes, exactly. So I mean, we can, yeah, you can name the system as you want. So S, A, B, and so on. Okay, so let us also calculate how Hadamard acts on the system if it was in a different initial state. So for example, let's say this the system was initially in a state 1. So yeah, can you calculate this? What will you get? Yes? Yes, exactly. We get the minus. The calculation is the same as for the 0. So we'll get just 0, -1, which is the minus. Okay, now let us see how does it act on the system if it was in the initial state plus. Yes, exactly. Does everyone see why it's the case? Yes.
Is it true that the main advantage of this system compared to the normal?
Can you speak a bit louder? Sorry.
Is it true that the main advantage of such a quantum system compared to the normal computer would be that it has infinitely many, uncountably infinitely many configurations compared to the Turing machine?
Okay, this is not a correct statement because so I mean when you have n qubits, right? So each qubit is a 2-level system. So the basis of this of the n qubits has 2 to the power n states. However, you should also take into, so it's not so basically yes, the difference in the number of possible states that we can encode in is polynomial, but you should also take into account that while the usual computation is deterministic, here the computation process is probabilistic. So you would get your solution, but with certain probability. So if we will have time, maybe we will talk about it in a course, but for the specific, but all the quantum computing examples that we will consider will be very simple, and we will not probably consider any algorithms. So to learn more about algorithms, I would recommend you to take the QIP course next semester. But yeah, basically, the statement that you made is not like entirely correct. Yeah.
I remember correctly, I think there's a proof that shows that quantum computers are Turing machines. So the quantum computer can't do anything. Exactly.
So yeah, I'm not so aware about this. So maybe is it the classical Turing machine proof or quantum Turing machine?
Basically saying that a quantum computer is like cannot fundamentally do things that a classical computer cannot do, and vice versa. So they're kind of like just like
Okay. Yes. That is the. I think that is the correct statement. It's just the. Then the question is how the complexity classes are connected, and so yeah, fair enough. Okay, then finally, how does H act on the system in the initial state minus? Yes, exactly. So by doing this simple consideration, there is one important thing that we learn about this operation H, that actually it can be used to convert between 2 bases. So one is the computational basis, and the other is the plus minus basis. So to convert between these 2 bases, we can just use this operation H. Okay, so this was our consideration of quantum circuits when it's only one system that we're considering. So what if we have several systems and we want to describe evolution of the several qubits? So this hasn't been yet talked about in the lecture, but there is a particular rule in quantum theory how we combine several systems. And the way we combine several systems is, so each system corresponds to a Hilbert space. So the states of the system are contained in this Hilbert space. And suppose that we have two systems A and B, and then we want to know how can the states of the joint systems of A and B be described. Like, for example, we have one qubit A, a second qubit B, and then we want to describe the states of the joint system A and B. So if system A has Hilbert space HA and system B has Hilbert space HB, then the joint Hilbert space is described by the tensor product of these two spaces. So what does it mean practically? So let me give you an example. So suppose that we have two systems, A and B, and already we'll start drawing them in a circuit. So we have a system A, then we have a system B. Suppose that their initial states for both of the systems they're both in a zero state. So we have this here. So the joint state then on the systems A and B, so can be written as 0A tensor product 0B. So how do we write this in a matrix form? So in computational basis, this is 1, 0 on A, tensor product 1, 0 on B. So then we just perform the tensor product operation, which is, so we take 1 here and multiply it by this vector. So be 1 by 1, 0. And then we take 0 here and multiply this by this vector. So we're going to be 0 by 1, 0. So we get the vector of 4 components. We'll get 1, 0. So this would be the first to 1, 0, and 0, 0. So this is going to be the matrix form of the joint states of the systems A and B. The same can be applied to operations. So basically, for example, let me take an example of, suppose we apply here the X gate. And the X gate you already, yes.
I'm confused. There's two vectors that are both identical. Like when you go from the tensor product to the 4-element
Yes.
vector, which one and which 0 comes from which vector?
Okay, yes, okay, so I'll make a bit more examples on that later, but let me consider this example. So we take the first component of the first vector and then multiply it by the first component of the second vector. So this we get this one. Then we multiply it by the second component of the second vector. So here we get here 0. So for example, if we consider a different example, let's say, yeah, before just we take 0 on A and we take 1 on B. Then this would correspond to the tensor product of 1, 0 and 0, 1. So here we would following the same rule, we would have 1, 0, 1 and 0, 0, 1. And here we get 0, 1, 0, 0. So actually, let's just do this as an exercise. So suppose that I consider a tensor product of state 1 on A and state 0 on B. Can you tell me the final vector? Yes.
It's twice.
So how again?
So it's top is 0, 0.
Yes.
And then you have 1, 0. 0.
Yes, exactly. That's right. Yeah. Yeah.
So is it just a chronicle product?
Sorry, which graph?
Is this just a chronicle product?
Yes, that's the chronicle product. Yeah. And finally, one by one. Yes. Yes, exactly. Also here we see that if we take these 4 vectors that we just considered, so 0 on A, 0 on B, 0 on A, 1 on B, 1 on A, 0 on B, 1 on A, 1 on B, just looking at their form, we see that they form a basis in this space H, which describes 2 qubits A and B. Okay, so does everybody understand how to do the tensor product? This is very important, at least for the vectors. Now we'll talk a bit about the matrices, which follow the same rule basically, but just a bit more calculation. Okay. Let us go back to our circuit, so AB. Which have some initial states. And suppose that we apply the X gate on the first qubit. And the X gate we have seen in a previous class, and also in the exercise sheet, if you looked at it in more detail. So the X gate is just this gate, 0, 1, 1, 0, which is also unitary. That's very easy to check. And suppose that then we want to write the action of this X gate as a joint action on the systems A and B. So how do we write this? So we want to write it as some unitary UAV acting on both systems. So in this case, we write this unitary as the tensor product of X on the system A and then identity on the system B, because we apply the operation X on a qubit A, and then we don't apply anything on the system B, which means that we apply an identity operation. Okay, how do we write this in the matrix form? So we have X acting on A, and then the identity on B. And here the same principle applies. So we take the first element of A and multiply it by the whole matrix B. So what we get here is the following. So we get 0 by 1 by this identity. Then we get 1 by this identity. Then we get 1 by identity. And then we get 0 by the identity, which gives us the following 4 by 4 matrix. So here we have 4 zeros. Here we have 1, 0, 0, 1. Here we have 1, 0, 0, 1. And here we have zeros. Yes.
There's one asking. So basically, when we basically have a circuit and we combine actions, we always write it down from the left on, first order action, then the second action, then the third action on each circuit, right?
Yes, a good point. So I haven't gone to it yet, but if you have several actions, I don't know, for example, we apply X, then you apply H, and the initial state is psi, then the final state, so let's say psi final, yes, so we start with psi, then we apply X, then we apply H. Was this a question?
No, the question was actually when you have, for example, these separate, when you have separate circuits, for example, where you apply one X, B, now let's say we don't have 2, but 3 or 4. If I write this quantum product, do I write the matrices from left to right when we go up to down?
Yes, 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 exactly, yes. So I mean, the order in which you write them is important also, so you don't kind of mix up the operations that you apply to them as well.
Okay.
So yeah. Okay. Okay, now let us consider a bit more involved example. So suppose that here I apply X, and here I also apply X. So how do I write it as a joint operation on both systems A and B? Yes?
X drawing the product X.
Yes. And can somebody tell me the matrix form of this? Yes.
It's basically the same as the previous matrix, except the ones and zeros in the top right and the bottom left are.
Yes. Yeah, basically it's going to be like this. Like the other diagonal thing. So is it clear for everyone how we perform this operation? Okay, very good. And then, so these were operations on individual qubits. So yes.
Is the tensor product unitary matrices always?
Yes, it is always a unitary. Yeah, this is very easy to check because so if we have a unitary in system A, tensor product with a unitary in system B, then basically, I mean, there are several arguments you can make. So first you can just write them out as a sum over the diagonal elements only. So here you only have diagonal elements, here you only have diagonal elements, which are all ones. So basically then the tensor product would only have the diagonal elements because you have this like 1, 1, 1, tensor product, 1, 1, 1. So basically this would be 1 by this thing that only has ones. 1 by thing that only has ones on a diagonal and so on. And all the others would be zeros. And basically you have on the diagonal of your big matrix also small diagonal matrices. So that would give you an identity matrix on AB. So yes, okay. So we were only looking at the so-called local operations right now. Why do we call them local? Because actually to perform, for example, this operation X on each qubit individually, we don't even need to kind of perform some operation on them jointly. So we can have A in one lab, B in the other lab, and just apply X's to them individually. So this is, we also call it local operation. What if we apply a global operation, which would be conditioned on both qubits. So it would act on the whole system. Let us consider one example of such an operation, which is also very important for quantum computing purposes. So it's called a CNOT operation, or a controlled NOT. So it is described as follows. So suppose that we have again two qubits, A and B. And then we apply to them a joint operation, which is usually drawn like this, which is described as follows. So if A is in a state 0, then we apply identity on B. And if A is in a state 1, then we apply X operation on B. So this is also sometimes denoted as like this. So this this dot here means that this operation is controlled on the state of the qubit A, and then it's connected by this wire, vertical wire, to the operation that we have performed on the second qubit in case the condition on the first qubit is satisfied. So for example, if the initial state of two systems is this, then the final state would be 0. And because A is in a state 0, then there is nothing happening on B. So it's still going to be B, 0B. Just one note. So usually when we write the states of the composite systems, we don't mention that we sometimes omit the tensor product, but it is implied that this is the tensor product of 0 on A and 0 on B. Moreover, sometimes what we write is 0, 0, AB. It's transformed to 0, 0, AB, where it is by convention the first label corresponds to the first qubit and the second to the second. Yes.
Sorry, I did not get what the dot means on the A line.
Yes, so the dot here means that we perform the operation conditioned on the state of the qubit A. So and usually the filled dot means that the operation is only performed if the qubit is in a state 1. And sometimes you would see kind of a non-filled dot like this, which means that the operation is performed only if the qubit is in a state 0. Okay, but let's continue to analyze the action of this unitary. So similarly, if the system A is in a state 0 and B system is in a state 1, then also nothing happens because system A is still in a state 0. Now, if A is in a state 1, then and B is in a state 0, then we know that if A is in a state 1, then we need to perform an X operation on B. So which state are we going to get in the end? So how does X act on the 0 state? Yes. Yes. So we're gonna get 1 on A and 1 on B. right? And finally, system A is in a state 1 and system B is in a state 1, then what happens? So yeah, we're gonna get 1, 0. So we can also write the CNOT operation in the CNOT gate. We usually just denote it as a CNOT. As the following. So now please ask questions if this is not clear. So we say that if the system A is in a state 0, then we don't apply anything on system B. And if the system B is in a state 1, if system A is in a state 1, then we apply an X operation on B. So this is, so do you understand what object is 0, 0? What is its matrix form? Yes?
If I need the one at the top.
Yes, exactly. And 1, 1. Yeah, it's similar. Yes. Yes, exactly. Okay, so since now you know how the tensor product works, can you tell me the final result of this? Yeah, you can take your time to calculate. Yes.
Why do we use something? Why do we have the matrix form of A, which is to show Y? Because I don't know.
Oh, here?
Yeah, why? For example, why not a state? Why not a constant? Why don't you see that?
So here, since we have this object, right? This is the matrix representation of the state 0 on A, and this will become important because when we introduce the concept of density matrices, which are also the valid description of quantum states, so the idea behind this, like mathematically, is just that you have two vectors which are this, right? And then you multiply them. If you multiply them, you get the matrix 2 by 2. Right, so the idea of matrices, which will come later in the course, is that it allows us to describe a bit more states of the system. So, for example, we saw from the previous exercise class that all states of a quantum system in a Hilbert space, all pure states, so to say, which can be described by these vectors, they all live on the surface of this block sphere. But one can also imagine systems which are described, the same system which can be described by a state which is within the block sphere. And this, to describe that state, we cannot use a vector. So vector is not sufficient. We need to use the concept of density matrix. And the idea of the density matrix comes from, so suppose you have some joint action on two systems like here, and then you discard the second system, you throw it away. And with that, you throw away some some information about the joint system, and you're kind of left with only states on the system. Let's say we discard the system B here, we only left with a system A. And so it is that we cannot then describe the state of the system as a vector. We need a matrix to do that. But this is a bit more advanced that come later in the course. So now we will only deal with kind of this pure state, so to say, which can be described by vectors. But then, for example, to write down this controlled operation, it's useful to kind of see this object 0, 0 ket bra. This might have been a bit confusing, so if it is confusing, you can discard my comment for now. Yeah, in the meanwhile, did anyone calculate this? Yes.
Basically, 1001 on the left.
Yes.
On the left, and on the right, upper corner the zeros, then on the lower right, to the left, and then the 0, 1, 0.
Yes, exactly. Very good. So this was the CNOT operation. One can also introduce other controlled operations. So, for example, this. So what this means is that this is an operation which is controlled on the state of the system A. If the system A is in a state 1, then only then this operation is applied. And then I can write this joint operation as, again, if 0 on A, nothing happens on B. And if it's 1 on A, then we apply the U on B. And for example, in the exercise sheet, you'll have this CZ operation, which is a control Z operation, where instead of X here, we would have a Z. Okay, so what is interesting about this CNOT operation is that it allows us to kind of start exploring the notion of entanglement and also how systems become entangled. So just to give you a brief intuition, so for example, let us make a simple calculation of how CNOT acts on a system in a particular joint state. So again, we have two systems A and B. And maybe this is also a good exercise to do now. So we have two systems A and B. And I will now draw a circuit. And you will evaluate the circuit, which is evaluating the circuit means that you will need to calculate the final state of the systems A and B. So what's the time? Yeah, we'll do this and then we'll go on a break. So a circuit, system A, system B, state 0, state 0. Here we apply a Hadamard gate. And then we apply a CNOT gate. So now I ask you to calculate the final state. So it's fine if you take time. Also ask questions if you have any. So just to warn you, this is important. So actually one of the exam questions is going to be about evaluating a very simple circuit like this. So, yes.
When we apply something like this, like control,
Gates, yeah.
gate, does the action, for example, because of the Hadamard gate, you might get a plus minus. You get a plus minus basically. So, and the control gate requires the 1 or 0, the computation basis.
Okay, good question. Allow me to alleviate this misunderstanding. So when I describe the action of the gates, yes, I describe it in computational basis, but it is a unitary. And the fact that it's a unitary does not depend on which basis we describe things in. So in the end, we just get this matrix, which is written down with respect to the computational basis, but it can be applied to any initial state, basically. It's just like, it's easy to see the principle of how this gate acts considering the example, oh, what if system A is in state 0? What if system B is in state 0, and so on. But otherwise, you just see it as a unitary operation, which can be applied to any joint state of two systems. Yes. Yeah, you can try to answer.
So I have all states are phosphate. So first of A is in phosphate because we have H gate, which transforms the basis. And then we don't change it. So only the B changes, and then one gate above, like H on both sides. So like H on B. By the H operator, the identity operator, you get the H operator, so that's why it's also cross.
I mean, here it's a controlled X, right?
Yeah.
I mean, okay, so your answer would be just plus plus. Okay, yeah, that's not correct. But does anybody have another suggestion? Yes. Yes, that's the correct answer. So, I mean, with the normalization factor, of course, but it would be 0, 0 on AB plus 1, 1 on AB. So what is the easy way to see this? So first we apply the Hadamard Gates. So we have the initial state 0A, 0B. We apply the Hadamard. Then we indeed get the plus on a system A and 0 on the system B. What is the plus? We can rewrite this as 1 over square root of 2, 0A, 0B, plus 1A, 0B. Then we apply the CNOT to this. And we can apply it, and since CNOT is a linear operation, so we just need to multiply the states by by this matrix, basically, we can just work on each state individually in the sum, since we know how CNOT acts on the qubits and computational basis. So here we have 0, 0. It would stay 0, 0, according to our analysis before. And then we have 1, 0, which would be transformed to 1, 1, because the operation is conditioned on the state of A, which is 1. So the state of B flips. We apply the X operation. So it's going to be 1, 1. And hence we get the state 1 over square root of 2, 0, 0 plus 1, 1. You will see the states very often when you work with 2-qubit systems. It is one of the states of so-called Bell bases, which you can introduce in the joint Hilbert state space of 2 qubits. What is interesting about this state is actually an example of an entangled state between 2 systems A and B. So here, what this means is that you cannot represent the states as a tensor product on individual states of A and B. So it cannot be written as a vector on A, tensor product, a vector on B. So here, actually, you can easily see it by just like taking 2 appropriately parameterized vectors for A and B, and then you'll just see that you cannot get these coefficients for their tensor product. Okay, now we go in a break, and please ask me questions if there are any. Okay, now. Yeah, let me wear the mask.
I mean, I'm.
No, I mean, it's just the rules. Sorry.
I just wanted to quickly ask. So basically, if we now measure this kind of state, basically,
Yes.
when we had a 50-50 chance of either getting both zeros,
Yes,
or of both ones.
yes.
Okay. Nice. On the last step in equality, like why?
Here.
This like the thing that is entanglement.
Yes, of course. I mean, this will be all easier seen when we go into the density matrix business, but here you can also see it. So you have a state. There's 0, 0 plus 1, 1. This is, let's say, the state. Yes, okay, so 0, 0.
Yeah, okay, it's 1.
One.
Yeah.
And then here. Okay. Okay. Then what I claim is that this is not equal to, let's say, AB, CD. With appropriate like this, A squared plus B squared equal 1, C squared plus D squared 1. So it's AC, AD, BC, BD, suppose that they're equal, right? Then what we get is, this is AC, AD is 0, BC is 0, 1 over square root of 2 is BD. Is it clear how I'll come to this consideration?
yes.
Yeah? Okay. Then from here we see that either A has to be 0 or D has to be 0. If A has to be 0, this cannot hold.
Yes.
If D has to be 0, this cannot hold.
Oh, I see.
So basically, we just have a state which still lives in the joint Hilbert space. So it's still a vector in the joint Hilbert space of A and B, this vector, which is normalized, everything is good, but it cannot be seen as a tensor product of individual vectors on two systems.
And what would what is that? Like, does this even? What does this even? What is this even?
Mean.
Oh, I see. Oh, so this would be.
This would be the.
Just trying to show two separate.
Yes. So, like you have systems A and B, right? And then you have different states.
Oh, I see.
Different states.
Okay, so this would mean we just that's just like a representation of two separate states.
Yes.
But we can't represent it as two separate states. So they're okay. Okay,
exactly.
Makes sense. Okay.
Yes.
Okay. Thank you.
So this is the concept of entanglement,
Okay.
which is very hyped about. Yes.
I have a question about the interferometer question from it.
Yes. Okay.
So there's the two states T and R about whether it's transmitted or reflected.
Yes.
But when, let's say we have the reflected one that comes here,
Yes.
do we have to change the label of the state because the reflected one will go that way for this path, whereas this path it would be the transmitted?
Okay, so no, we always work kind of in the same basis, so 0-1 basis.
Mhm.
It's just like both of these interferometer correspond to the certain action that we apply to them. So, so for example, like, yeah, actually, I was going to explain it in the next hour, but
Okay.
But yeah, basically, you just have the incoming beam, which is in the 0-1 state,
Mhm.
0-1 state, and then this action of this interferometer can be seen as a Hadamard state, Hadamard Gates.
I mean, I've calculated that
Yes.
and I get the same thing, but I'm just wondering about whether we would have to do a change basis.
No. I mean, we always choose the basis we work in the beginning, and then we don't change it.
Okay.
Basically.
Thank you.
Yeah. Yes.
So the CNOT gate, we just write it as a tensor product array times that
Yes.
identity operate
Yes.
gate, which does nothing, and a tensor product of the other thing and the Hadamard gate. What was the point of this?
No, this is not a Hadamard. This is an X gate. Yeah.
So this gate is CNOT is entangled gate by definition.
It's an entangling gate. Yes.
So what is the point of splitting it into some?
This is just an easy way to see how it acts on different states. So basically, from this form, you can see that, for example, you take this form, and then you act on a joint state. For example, A is in the state 0, and B is in the state whatever. Then, yeah, I can write this out actually. So we just have our 0,0A identity on B plus 1,1A X on B. And then we act with this on 0A tensor product, I don't know, say 1B, right? So if we have if we have some UA, UB acting on psi A, psi B, then this can be written as just UA acting on psi A, tensor product UB acting on psi B. Oh, we're always allowed to do that.
I mean, the tensor product is not always associated. Yeah, but I think here the dimension.
No, I mean, here we always make sure that this dimension corresponds to this dimension to this dimension. So, I mean, we're only talking about physical situations. So, yeah. And here, so basically here, what we get is that, so the first term, 0, 0 would give us 1 because 0 is normalized. So we only get the 0 here. And then acting identity on B, we get 1 on B. And that is the only term that survives because here we get ket raw 1, 0, which is 0 because 1 and 0 are orthogonal. So basically we get 0. So we get. So you see that only the first term survives. Okay. So. Okay, let us continue. So let us now, so now we were talking about just like this applying gates, and we thought about like applying gates as a very mathematical procedure, but then there is also a way to, like, several ways to how we implement this in experimental settings. So one way to kind of create, show the application of a Hadamard gate is to use so-called Mach Fender interferometer. So here we will describe its action in a very simplified form. Of course, it's all a simplification, but for our purposes, this will suffice. So the main element of the interferometer, I can take off my mask as well, is so-called beam splitter. And the beam splitter is a semi-transparent mirror which splits the beam of light into two beams of equal intensity. So one is reflected basically, and the other one goes through. And suppose that we don't consider the whole beam of light. We just consider one photon in this beam of light. And one photon can be seen as, in this case, as essentially as a qubit, which has 2 degrees of freedom. So either it is transmitted or it is reflected. And basically then we can describe, so first let me draw this beam splitter. Is there any color chalk? Okay. So we have this beam splitter, which is usually drawn like this. And there are 2 beams, one which is reflected and one which is transmitted. And for example, when a photon hits this beam splitter, and we describe the photon in this basis, which we label as R and T, but this can be seen as just this computational basis of 0, 1. We just use different labeling. And the initial state of the photon is T. Then after going through the beam splitter, it ends up in the superposition, in the equal superposition of the states T and R. So this is just describing the action of the beam splitter. And then we also know that if the initial state of the photon is R, then we also end up in a superposed state of T and R. It's just like there will be some additional phase on the state R. So the first question to you would be, which I already kind of spoiled, is, so if we draw this as a circuit, so we have our photon, some initial state, and then we apply the beam splitter. So let me just write down that this is a beam splitter. So what is this operation? So we know that it transforms the states as here. And let's say that this is a 0 state, this is a 1 state. Which operation? Yes?
We can represent the operation there with the Hadamard Gates.
Yes, exactly. This will be a Hadamard gate. which is, remind you of this. So why is this like this? Because if we just think of t as a 0 and r of 1, then we just arrive here to the plus state, and here we arrive to the minus state. So this is an operation which transforms 0 to plus and 1 to minus. Yes?
So why is it that goes to beam splitter if it goes in interpretation?
So why does it go to?
So the photon goes through, so if it starts in T, it goes to beam splitter, why is the state is in whatever flow? Why is it not different? Just see, like, why does it not keep the same property?
Going to the beam splitter. Okay, it's just like this is just the property of this mirror, that it partially reflects the beam and partially transmits it, basically. Yeah, this is due to the properties of the material, essentially, that it's made of. But here, like, we don't go into that detail. Usually, like, these details are considered in like optics course, like quantum optics course, or some engineering courses maybe. But here, everything that we need to know is just that the action of this device can be seen as following. Okay. So let us maybe come to the interferometer itself. So now let us take two beam splitters. So we have the incoming beam, then we have the first beam splitter, and we have two beams which is transmitted and reflected, and then we want to join them together back. And for this, so there is an additional element in this setup, which is we just put a mirror which fully reflects this beam here. And we put a mirror here, which fully reflects the transmitted beam. And then we put another beam splitter here. And coming out of this beam splitter, so the beam can possibly come out in this reflected direction or transmitted direction. And here we have two detectors. So this is a general setup of the interferometer. So the mirrors here, they don't play any role except for the redirecting the beam, so they would meet again at this beam splitter. So as we saw, the action of one beam splitter is a Hadamard, right? So how would you draw the action of this interferometer as a circuit? Any ideas? Yes. Yes, exactly. The first Hadamard, the second Hadamard, and then finally, when we come to the detectors, so the detectors correspond to the measurement. And the measurement in the circuit is usually drawn as this rectangular box with a meter inside. Yes?
So we will see two vectors as one measurement.
Yes.
For one, basically which vector goes up is decided either the reflected state or the transparent state.
Yes. Yes. So for example, here in this very simple setup of interferometer, which we can actually make a bit more complicated, but for now we'll just look at this. The action of this interferometer is an identity, because so whatever state you input, you're gonna get the same state here. Why? Because H squared is equal to identity, basically. So here, this circuit does not do anything. Yes?
So in the beginning, before the photon hits the beam splitter,
Yes.
do we consider it reflected, or do we consider it transient parallel? We consider it just in between, and we just don't know what it is.
So even before it hits the beam splitter, it can also be in a superposition of two states. So generally we would write the initial state as alpha 0 plus beta, sorry, alpha transmitted plus beta r. If it's a bit difficult to understand the kind of this TR notation, you can just substitute T by 0, R by 1, and then you end up in this usual kind of qubit consideration of things. So for example, just to make sure you understand, suppose that, like, if this is a T, so if the initial state of the photon is T, then the final state would also be T. And then I measure in the TR basis, and then only one detector will click with certainty, and the other will never click. However, if, for example, I start in a state 1/squared of 2t plus r, when I measure, in half of the cases, one detector will click, and in half of the cases, the other will click. Yes.
If you only apply this one H to one, that means whatever we measure is not actually what was in the, like whatever we measure is not actually what we wanted to measure, because it's something different. That's why we have two H states. Go back to Earth.
Yes, that can be seen. So, yeah.
The reason we have this in the first place is that we can't use the, we have to split the beam to determine the for example, like why would we the measuring device at the very beginning, like why change the state twice before measuring the actual device? You don't have a device, or
so I mean, so here the reason that we apply the H twice is that that we need to kind of take two beams together to see possible interference effects. So, for example, we will see that if we just add some action on one leg of this interferometer, so just the kind of notation is that these two directions are called legs of an interferometer. And so, for example, here, if we add something that kind of slows down this beam, then this would result in the fact in kind of in a phase difference between two legs, which would then lead to the interesting effects on this end.
my question is more H is the identity why you thought of it in the first place. Why not just use the measuring device in the very beginning?
So yeah, so I mean, yes, you can do that. Here I'm just explaining this setup, and now we will tweak it so that this would applying. So there would be essentially some action in the middle, and then then these two Hadamards would be squeezing some other operation in the middle, and then this would obviously be equal to the identity operation.
Is it even possible to measure the state like this with the interferometer? Because the way I understand it, we have to SQuID to measure something. So my question is, there a measuring device to measure the same thing without having to SQuID in the first place? Because the setup, the way we have
I mean, so
detectors, right? But it's
yes.
just one photon that cannot be exposed to one or the other.
Or, I mean, here you just have two directions, right? So basically, I mean, okay, so I'm not an experimentalist, so, but the thing is that for me, for example, the fact that, okay, we either have a measurement here, right here, or we have the measurement and in the end. For this particular process, it's similar. It's the same. So here we just have these two explicit detectors drawn because they correspond to kind of different directions of the beam. So, and here, for example, the way I draw this beam here, it's only one direction. So in the end, that would correspond to it going directly to the DA. But here, we also think about it as just beam splitter kind of affecting the degrees of freedom of the photon. So it basically kind of makes a superposition of 2 degrees of freedom, sorry, of 1 degree of freedom.
Explain what happened. So you said that we have a initial space superposition out there.
Yes.
The chances are 50-50 to go in either direction.
Yes.
Can you maybe elaborate why that's the case for the C1?
So if we start with this state, then basically this corresponds to this identity, right? Here, and then the final state would be, in this case, T plus R. And then you can think about the detector DA, kind of reading out the result of the measurement if it's T, and the detector B reading out the result of measurement if it's R. So basically, we conduct a measurement. If we measure T, then A clicks. If we measure R, B clicks. And then if you have such a state and you measure it in this basis, then in half of the cases, so the probability of measuring T, let's say it would be according to the Born rule, just psi T modulus squared. And this is 1 over square root of 2, so it's going to be 1 over square root of 2 modulus squared, which is 1/2. And the probability of measuring R would be similarly psi R squared, also 1/2. Is this more or less clear? Okay. So now let us tweak. Let us introduce a phase shifter. So now we consider that here we have some operation, like, yeah, phase shift. So basically here, if the photon is in that lower leg, then we install some polarizer there and we change its phase. So this also can be written as unitary, acting on the photon. So we know that the phase shifter acts in the following way. So if the photon is in a state T, so let us call this phase shifter as an operation S. So if we apply this operation S to the photon in a state T, so it kind of corresponds to the photon being in a lower leg. Then there is a phase shift of, let's say, phi, which we describe as e to the power I phi t. So basically the state stays the same. There is just some additional phase. And then if we apply it to the state R, then we get the state R back. So nothing happens. Yes, can somebody tell me what is then the matrix of this unitary? Just intuitively, yes.
E to the I phi the top left and the 1 on the bottom right.
Yes, exactly. Very good. So you can still think about T as a 0 and R as 1. And then this is basically what you get. It's like almost identity, but there is on one of the basis elements, there is a shift. So it kind of seen as an this complex coefficient. And then the circuit of our interferometer can be modified as, so we still have the Hadamard here as a beam splitter. Then we have this phase shift. And then we have Hadamard again. And then we have the measurement. Okay, so now let us do a simple calculation. So suppose that the initial state, psi, is T. So to calculate the final state before the measurement, which we need to know because we want to know the statistics for the measurement and in how many cases the detectors would click. We need to apply, so we have our initial state T. So first we apply Hadamard, then we apply phase shift S, then we apply Hadamard. Okay, so how do we do this? Let me show maybe this in a matrix form, because we can always do things in a matrix form. You can also just do it in a bracket form. But let me start with a matrix, since I haven't, I don't think I have done this explicitly. So first it's the Hadamard. Then we have the phase shift. Then we have another Hadamard. Sorry, and then we apply it to the system in a state T. Just 1, 0. Okay, so let us do this step by step. So here we have 1/2. So this is going to be 1, 1, 1, minus 1, e to the power I phi, 0, 0, 1. Then we act with the Hadamard on 1, 0. What we get is 1, 1. Okay. Now we act with a phase shift on 1, 1. So here we still have this. Then here on a first component, we'll get to phase shift e to the power I phi. And on the second component, we will not get anything. Okay. And finally, have 1/2. And here we have the following states. It's going to be e to the power I phi plus 1. And here e to the power I phi minus 1. So basically, now we can rewrite this in a bracket form. Sorry, in the cat form. We will get e to the power I phi plus 1 over 2 t plus e to the power I phi minus 1 over 2 r. And you see here that actually now the phase shift makes a difference for the statistics of the measurement that we conduct here. Why? Because, so what is the probability of measuring t? Yeah. Yes. So the squared, right? So what is the squared? So here we can kind of take out e to the power I phi over 2, and here we are left with I phi over 2 plus e to the power minus I phi over 2 over 2 squared. So this we cannot consider because we take modulus squared anyway. And this is actually a cosine of phi over 2. So basically what we get here is cosine squared of phi over 2. And similarly for the probability of getting r, it's modulus e to the power I phi minus 1 over 2 squared. And this is going to be, well, one easy way to calculate this is just say it's 1 minus the probability of measuring t. So it's going to be sine squared phi over 2. Or you can do the same thing as here, take out e to the power I phi over 2 and come to the same conclusion. Basically, because then you will get a sine. So here we see that introducing this phase shift on one of the legs, which corresponds to this unitary operation, actually results in a meaningful change of statistics. Yes?
Why could we remove I phi in the...
Yes. Okay, so if we have two complex numbers, a and b, and we take the modulus of them, then this is equal to just modulus a multiplied by modulus b. And for example, if a is e to the power I phi, then we get that this is modulus e to the power I phi by modulus b. And modulus e to the power I phi is 1. Yeah, exactly. So we'll just get b. And yes, and this is a cosine because for a general case, cosine alpha can be written as e to the power I alpha plus e to the power minus I alpha over 2. And this is the case because e to the power I alpha is basically cosine alpha plus I sine alpha. And e to the power minus I alpha is cosine alpha minus I sine alpha. And this is over 2. And then I sine alpha goes away. And you're just left with cosine. And it's the same for sine, except for the sine alpha. You would have e to the power I alpha minus e to the power minus I alpha over 2i. Yes.
Finally, the P here is that the P stand for the projector or for the probability?
It's a probability. Yes. So usually the big P stands for the probability, and for the projector, you can also use a big P, but usually we use the pi for the projector. That's notation wise. Yeah. Okay, so this was basically the third exercise. And now we have like 5 minutes. Let me spend 5 minutes on the quantum computing exercise, which is not compulsory. If you want to try it, you can try it out. Yeah, it's not going to be part of the exam in any way. Basically, there are two ways. So either you install one of the languages that you like, and there are many, like there's Q# from Microsoft, Qiskit from IBM, Project Q, which was developed at ETH. There's also high-level ones like Silk and so, which is also an ETH creation. But from my personal experience, installing them even on a virtual machine is very annoying, and sometimes like they require different versions of Python, like different packages and so on. So what I recommend you to do is to use this StrangeWorks website. And there, it's basically like Code Academy. So you can just run your codes in any language you like that they support, and they support most of the languages. And there is a library with different tutorials. And then you can choose a tutorial and try to run a very simple circuit. Like for example, so basically the way most of this languages work is that, so usually you have a header, which is, I include this engine, I include this compiler, I include this package, which has all the gates descriptions that I need. And then the first thing that you do is then you allocate qubits. So there is a particular operation for allocating qubits. So for example, if you only want to have 1 qubit, then you allocate 1, 2, you allocate more. And then basically you just write down the operations that you apply to the qubits in the order that you apply them in a circuit. Like for example, if you find a tutorial there on the Project Q, it's described there how to apply a Hadamard gate to a qubit, how you write it out. But basically it's usually, you allocate a qubit and then you say, gate Hadamard gate, apply to the qubits that you allocated before, like declared before. So I would advise you to maybe try to play with any language that you like. They're usually all very accessible, and there are also tutorials on their dedicated websites. And I think some languages like Qiskit also have a huge following, and there are like lots and lots of educational material. For now, and also in this course, we will not consider any algorithms. So maybe the one algorithm that we will try to consider is the quantum teleportation algorithm. But there are no like this famous algorithm which are like better than the classical, which are claimed to be better than the classical ones. So for this, you would need to attend QIP. For now, I would just advise you to try maybe to implement the circuits that we've seen today in one of the languages. And for example, try to create this entangled state 0, 0 plus 1, 1, and then try to measure it in a computational basis and see if your predictions match what the software is telling you. Okay. Yeah, I think I'm done for today. Any questions are welcome. Thank you for attending, and I think there is a lecture following, so that's it. Yeah, just let me turn off the mic and then I'll be available.